Welcome to The Explainer. Today, we've got something pretty wild for you. A paper that finds an absolutely shocking connection between the fundamental building blocks of our universe and, believe it or not, our laundry.
I know, it sounds like a completely random question, right? Like the setup for a really bad science joke. But this is the exact question a 2006 physics paper decided to tackle. And you're going to want to stick around because the answer is actually kind of mind-blowing.
All right, so to unravel this whole mystery, we need to start with something we all remember from science class, the good old periodic table. For more than a century, this chart has been our main map to the chemical world. And look, it's great. It organizes all the elements by atomic number, groups them by their properties, it gets the job done. But, and this is a big but, as a way to actually visualize the relationships between the elements, it's kind of broken. Here's what I mean. Just look at it. You follow a row all the way to the end, say to neon, element number 10. Okay, so where's number 11, sodium? It's all the way back on the other side of this giant, awkward gap. The continuous path is totally broken. The whole layout is based on these, let's call them designer decisions, where humans decided to cram the elements into this specific grid instead of letting their natural connections shine through. And this is where that 2006 paper by physicist P. Fraundorf comes in. He looked at this old problem and asked a really simple but totally radical question. What if we just stop trying to force all the elements into a neat little box? And that is just a beautiful idea, isn't it? Instead of a rigid grid, just picture this. Every single element is a tiny bead. And you connect that bead to its neighbors with identical little springs. And then you just let the whole thing go. You let physics itself find the most natural, relaxed arrangement. The process itself is so elegant. You take all the elements, you link them up to their neighbors with these imaginary springs, and then you just let the entire network settle into its lowest energy state, its happy place. No more human meddling, no more designer decisions, just pure physics doing the driving. So the big question is, what happens when you run this simulation and let this whole network of elements settle down? What shape does it actually want to form? Well, first, as a little test, if you force the model to stay flat in 2D, you get this really neat orderly spiral. The elements just coil around each other, no lines crossing. It's a cool pattern for sure, but it's not the main event. This is just the warm-up. The real magic, the really interesting part, is what happens when you take off the training wheels. What shape emerges when you let that whole network relax freely in three-dimensional space? Okay, so get this. It doesn't just clump up into a sphere or some kind of random, messy blob. Not at all. It actually unfurls into this complex, sheet-like surface. And the most important feature of this new shape isn't all the twists and turns. It's the fact that it has holes in it. And here it is, the incredible result. The shape it makes is not random. It has a very specific fundamental property. It doesn't have one hole, or two, or four. Every single time you run the simulation, the network always relaxes into a surface with exactly three distinct holes. That number, 3, it's like a hidden rule, a secret code governing the shape of all the elements. So, 3 holes. Why is that number so important? Well, this is it. This is where the whole thing comes together, and we finally get the answer to our t-shirt mystery. First, a super quick concept, topology. Don't worry, it's simpler than it sounds. In math, topology is just the study of a shape's most basic properties, like how many holes it has. So, to a topologist, a coffee mug and a donut are the exact same shape. Why? Because they both have one hole. You could squish and stretch a donut into the shape of a mug without ever ripping it. And that brings us to the final amazing connection. What's a common, everyday object that is defined by having exactly 3 topological holes? You've got 1 for your neck and 2 for your sleeves. The network of all known elements, when it finds its own natural shape, forms a t-shirt. This insight is the whole key. Because the shape is topologically a t-shirt, you can actually unfold it and lay it flat without breaking any of those spring connections. And what you get is a brand new, completely connected 2D periodic table. And this isn't just a gimmick. This t-shirt table actually fixes the biggest flaws of the old one. The path of atomic numbers becomes a single unbroken line that snakes through the whole chart. All the connections between elements are visually right there. And those awkward gaps, they're gone, replaced by the holes of the shirt. It all just fits. The paper even suggests this discovery isn't just for chemists and physicists. It could inspire all sorts of fun cross-disciplinary projects, mixing science with art and design. I mean, can you imagine a design class being tasked with creating a beautiful, functional periodic table that follows these topological rules?
And that brings us right back to the start. The big takeaway here is that by letting the elements decide for themselves, we uncovered this hidden, elegant structure that connects the building blocks of matter to our clothes. It's a powerful reminder that sometimes the most profound answers are found just by looking at old problems in a completely new way. So the next time you put on a shirt, maybe you'll think about the universe just a little bit differently.